All right, the topic for this video, we're going to kind of continue talking about the different bonds that chemical elements make. All right, and you remember from last time we talked about the covalent bond, the polar covalent bond. In a separate video, I also talked about ionic bonds. I'm going to concentrate a little bit more on the hydrogen bonds now, and I'm going to revisit the polar covalent because the polar covalent bond is going to be important in establishing our hydrogen bonds. Okay, so when I talked in the last video, I had our oxygen and our hydrogen. That chemically makes up our H2O, right? And H2O is just water, all right? But water is going to be very important biologically. And when we talked last time, I said there was a slight negative associated with oxygen. There's a slight positive associated with hydrogen, okay? In terms of what's going on there, when we talk about oxygen, oxygen is more electronegative. And all electronegative means is it has a slight negative charge associated with it. So remember, oxygen is our selfish kid. It's kind of pulling those electrons away from hydrogen, but hydrogen doesn't want to completely give up that electron because otherwise then that's going to mess with its outer shell, okay? And it won't have a complete shell. So hydrogen pulls back and says, no, I need to keep some of that. So our hydrogen is going to have a slight positive charge. Oxygen is going to have a slight negative charge. That's our polar covalent. Oops. Let's see. We'll just erase that and spell that correctly because spelling is important. All right. Our polar covalent bond. And having the slight positive and negative here, what that's going to do is when you have something like water that's in solution, meaning it's aqueous or liquid, we're going to have those slight positive and negative charges are going to connect. We can put another one here. Like that. Let's put an oxygen over here with another water molecule. Our negatives and our positives. All right. And if you notice, I kind of drew the bond for the hydrogen bond a little bit different than what I've drawn some of the others. If you notice, I used dots this time. And the reason I use dots is because that slight positive and that slight negative, that's a very weak interaction. So it's akin to what you've got going on with the ionic bonds, like with sodium and chloride, but it's not quite as strong. So the hydrogen bonds that are made in a solution of water very easily make bonds and very easily then break bonds. And some of what you're going to get there with the making and breaking of bonds is going to have to do with how close the molecules are together. All right? And if you notice, I didn't draw anything very evenly because when we're talking about aqueous solution, you'll have some variable distance between the molecules that are in water. All right? Whereas if we look at a more regular structure like ice, which is just frozen water, because the temperature is lowered, it creates a uniform distance between all of the water molecules, all right? And that kind of stabilizes things a little bit, all right? But in terms of that, our hydrogen bonds are going to be our weakest bond. And these are very easily made and broken, all right? And in terms of that, water is going to be one example where this is going to become important. Another example where hydrogen bonding is going to be important that we're going to get to this semester is going to be with the DNA double helix. Because that DNA double helix has to have the ability to pull apart during DNA replication. So what holds the two strands of DNA together is going to be hydrogen bonds. Now what holds each strand together in DNA are going to be covalent bonds. So if you notice with the water here, I drew a straight line. This is going to be a covalent bond. Again with spelling in me. It's okay. In terms of what you need to know associated with this, all right? I want you to understand the differences between the strengths of the different bonds, how they are working. Hydrogen and ionic bonds are working more on charge. Polar covalent bonds are sharing electrons, so it's going to be a stronger bond, okay? And in terms of the properties associated with water, the reason I like using water for this example is water is essential for life, all right? Now, water in and of itself is not alive, but living organisms require water in order to survive. This is part of that interaction that we were talking about in Chapter 1 between the living and non-living elements associated with an ecosystem. With life, at least here on Earth, we need water as part of the environment for life to continue, okay? But water is not a property associated with life. So that's a kind of a distinguishing difference I want you to take away from this. It's essential for life to continue, but it does not define life, okay? So that's going to be one reason why it's important for you to understand kind of what's going on with water. The other thing that's important in terms of biological systems water is going to be our main solvent, okay? A solvent, when we're talking about chemistry, is something that you dissolve something in. So, for example, if you had a cup of coffee this morning, the coffee would be your solvent, okay? The sugar maybe that you put in your coffee would be the solute, okay? So in terms of solvent, we're talking about something that is liquid, okay? The solute typically is going to be something that's going to be solid, okay? So it needs to dissolve into the solvent, and by dissolve, when you're mixing that cup of coffee, the sugar gets distributed within the solvent, okay? So that's an example of a solvent and a solute that you might have experienced today. In terms of biological systems, any time experimentally scientists are using solutions, okay, and a solution is just a combination of a solvent and a solute. So your coffee with sugar would be an example of a solution, all right? Water is going to be our main solvent for making any solution biologically, all right? There are plenty of other solvents that can be used chemically. Alcohol would be an example of one, but typically with biological systems, we don't use alcohol as a solvent. Most of our solvents in biology are going to be water, and part of the reason for that is the polarity that's associated with water. The water is polar, all right? And when we say water is polar, it has to do with the distribution of charges and having one of the elements within that compound be more electronegative than the other, all right? So hopefully that made sense. If you have any questions, please let me know. All right, thank you for your attention.